the area problem. So this is continuing with just like what are the problems encountered in calculus? Like why are we doing this? What are we working towards? One of the things I need to tell you is like we just talked about the secant line problem, and we talked about like, okay, so how do you take your result from the secant line and turn it into a result about the tangent line? That's going to be one of the main driving problems we have. You're going to see that there's a similar sort of thing with the area problem. And in fact, that's basically what calculus is. Like, it's about taking something like what your result from the secant line was and turning it into the result that you want, i.e. the tangent line. So how do you take your secant line result, turn it into a tangent line result? The first part of what we're going to talk about is limits. That actually shows you how to do all of that, which we'll get to that later, but I'm just sort of telling you, like, we're talking about this now so that it makes intuitive sense later about, like, why am I doing all this stuff? Like, I don't see the point of it. Like, the point of it is to solve these problems that we're talking about from the get-go. Okay, so let's put in our graph here. Okay, difficulty. There we go. Got your x and y axis. And let's say that you have a line. Line looks like this. That's your function. So there's your f of x. Okay. And let's say that right here is x equals a, and right over here is x equals b. What we want to know is this area bounded here. Okay, so we have a description of this area. It is the area under f of x between x equals a and x equals b, and finally above the x-axis. So if you think about it, this description shows you that green region right there. It's above the x-axis, it's below the line f of x, and it's between the vertical lines x equals a and x equals b. Okay, this is actually pretty easy to figure out if you remember any of your basic geometry formulas, because what you can do is split it up into two regions. We'll call this region 1 right here. What shape is region 1? So looking at that, like we've got region 1 in blue. Yeah, exactly. So it has some height, which we'll call h. You could figure it out by plugging in a into the function, right? The height of this, actually let's just call it f of a. Right, the height of that is f of a. Now how wide is it? How far is it from here to here? How wide? Do we know how wide it is? If you're going from A to B, how far is it between A and B? Do we know? I'll just tell you. It's a B minus A. No, AB would be, you want the difference between them. So if you ever have like, here, let's just like draw it on a number line. You can like see that it works. If this is 1 and this is 5, how far is 1 from 5? 4, and that's equal to 5 minus 1. Okay, it always works. The distance between two numbers is you take one of the numbers and subtract the other number. That'll give you the distance between them. Okay, so either way, the fact is, what I'm trying to point out is that the area of 1 is just the height times the width, which is f of a times b minus a. Right? That's your height. That's your width. Okay, now you have another region. Let's call it region 2. Let's put it in red. what shape is region 2, the leftover? It's a right triangle, right? And basically, the height of that so let's just write this down. You get area 2. The height of that rectangle is f of b minus f of a, right? Because you can plug b into it and you get the height right here, and then you subtract the height right there. You want that height, that would be f of b minus f of a times the width, which would also be b minus a, and then half of that from the rectangle formula, right? Because you get 1/2 of base times height. Okay, so boom, like if you're looking for the area under a line, it's pretty straightforward to figure that out. You're going to break it up into a rectangle and a triangle. Boom, not hard at all. Okay, like it shouldn't be mind-blowing, right? Just like how if you're going at constant speed, you always know at any instant how fast the object is going. Now, what becomes more complicated is when you have like a curvy graph. Say that this is now your f of x. And you have x equals a right here. And you've got x equals b right here. The area you want is this stuff. But can you split this up into elementary shapes? No, because you have that stupid curved top. Like, you could possibly break it up into a rectangle. You'd get like 2 regions, right? This rectangle, and then you'd have this stuff up here. But that stuff up there, it has that curvy top. You don't know how to calculate it. Okay? So you're like, holy shit, like how do I find this area that I want here? Well, it gets a little complicated. But what you realize is that you can approximate the area. With rectangles. So I'm going to copy this. So I don't have to like redraw. Oops. Let's copy it. Let's paste it over here. And this is so amazing how you could do this. Isn't that pretty cool? I don't have to like redraw the whole thing. I like really love this. Okay, so let's erase some of the stuff. We don't need all this stuff inside here. Okay, so we're interested in this this stuff. So what you could do is say, I could take my region, my area between A and B, and let's split it up into 4 parts. So I could draw a line in the middle, so I could half it, and then I could half it again. And what you can do is start drawing some rectangles. So let me draw it like, here, I'll draw a rectangle like this. I'll draw a rectangle. Okay, why is it not letting me do it? Let me draw rectangles. I want another one, but the height needs to be a little different. And then I want another one. Let me do it. There we go. Height will be like that. And then another one too. Like so. Okay, so I'm gonna like fill this in so you can like sort of see what I'm doing. You can see, hopefully see that I've filled in the rectangles. Looking at those rectangles, how decently of a job, if you were to add up the area of those 4 rectangles, how decently of a job would that do estimating the area that I want? Like, real talk. Like, how would you describe it? Like, horribly, decently? I'm going to zoom in on it so you can see it a little better. Pretty cool how you can't do this in a board normally, like in the real world. Okay, so how decently of a job do the rectangles do estimating that area? Right, but there is sort of a problem with it. Like, let's look at this rectangle, right, the first one. What's happening with the rectangle and the area that I want to estimate? Like, I sort of highlighted this little gap right here. What's happening in this white gap? Yeah, so in other words, this is called an underestimate. The rectangle is a little too small. Do you get what I mean by that? Like, it's too small, it's an underestimate. What happens right here and right here with the rectangles? Yeah, exactly, it's too big. And then finally, last one, also a underestimate. But this is actually the really cool thing about this. What do you notice about the under and over estimates? Like, if you look at them, like something nice is happening. Like, some of it's too small, but some of it's too big. But what seems to happen? Yeah, so like you want to sort of say that because one underestimates the amount approximately equal to the overestimated amount, like it's like they cancel, right? The amount that we go over on one cancels out with the amount that they go up over. The amount that we go under cancels the amount that we go over, right? Oops, I put that where you couldn't see it. So it sort of cancels. And this actually ends up working out for us, basically. Usually this is what happens. You take your approximation so we call this a 4 rectangle approximation. We would say it's an n equals 4 approximation. And it's like not that bad. Like, it's working for us. The amount that's underestimated is pretty close to the amount that's overestimated. So it's probably going to be pretty close to the number that we want. Okay? And if you really wanted to fix this, what you could do is start making smaller and smaller triangles. So I could make a triangle like this. And then I can make a triangle. Oops. Okay, I want another one. Sorry, that's my dog. But anyways, what you could do, I guess I'll just draw it in myself. Dying. You could start breaking your region up into smaller rectangles. And what happens is that as you start adding more and more rectangles, the amount of overestimate and underestimate gets bigger. Okay, so what we'll be doing is taking our approximation with rectangles, and you can get it pretty close to the actual area by just adding more rectangles. And then what do? You just add together the areas. And remember that each area is a base times a height. The height of these rectangles will be determined by the function. And then the base is some number. Let's just call the base b. As you add more rectangles, what happens to this base? Like the width of the rectangles? Like as you add more rectangles, what happens to the width of the rectangles? That's a good question. So you can see, like with the 4 rectangles, they were each this wide. As you make more rectangles, what happens to their widths? Yeah, and actually that's a problem for us. If you want an infinite number of rectangles, then the widths would be 0, and then that becomes an issue. And this is actually something that we're going to grapple with later. Because what ends up happening is that if you make a bunch of infinitely small triangles, it actually like perfectly fits the area as the idea. But then you run into an issue because if you have an infinite number of rectangles, then they all have to have 0 width. But if they have 0 width, then they have no area, and you can't add it up anymore. And that's like going to be something that we discuss down the line. It's actually pretty cool. Okay.